Hi class, and welcome to our last lesson on chapter 13. We're on 13.5, talking about more measures of center today. And just as a way of review, the center of a data distribution, we have three different measures of center. The mean, that's the average. The median, that's the number that's in the middle. And then the mode, and that's the one that occurs most often. So we're going to talk about more of these three measures of center in this video lesson today. First thing I want you to do is here is some data on the 2013-2014 Miami Heat basketball players. Okay, so if we take a look at these salaries here, I'm going to put them in my calculator, and you can watch me do that here. If I pull up my calculator, stats, edit, and I've already listed all of them in there, so 19 million, 19 million, and 18.5 million, so on and so forth. If I find the mean and the standard deviation of that, or the mean and the median, sorry. So if I go to calculate number 1, and I want it for list 1, so I'm good to go. Take a look at the mean here. The mean is 5.16 million. 5.16, that's the mean. And the median, the one in the middle, is 1.5 million. Let's write that down, 1.5 million. So the median is 1.5 million. And the mean was what again? 5 point something, I think. 5.16. 5.16 million. 5.16 million. So the mean and the median are both measures of center. They should both get you the center of the data. Why are they so far off? I mean, $3.5 million, that is a big difference between the mean and the median. Why are they so different? And the reason why they are so different is because of the outliers. Outliers strongly affect the mean, so it really drags the mean towards the outliers, and the outliers are the big salaries. LeBron James, as well as Dwayne Wade and Chris Bosh. These ones are really pulling the mean, and you'll see that here on these upcoming slides. So that's the reason why they're so different, is because of the outliers. So outliers strongly affect the mean, but they don't affect the median as much. They strongly affect the mean, but not the median so much. And if you think about it in this way, the median, you know, if we have 9 data entries, 1, 2, 3, 4, 5, 6, 7, 8, 9. The median isn't very strongly affected by outliers because it doesn't matter how high this number is or how low this number is. They just get crossed off, and number 5 is the median. So that's why a huge, crazy large number doesn't affect the median as much, because it just gets crossed off with the lowest number. So that's why the median isn't very affected, whereas the mean is very affected, because instead of just crossing them off, we're adding up all of these and then dividing by how many there are, so it matters how big this number is or how big this number is. So if there's an outlier, that strongly affects the average because it's added into the total. So that's a big deal. It doesn't affect the median as much because it's just crossed off with the lowest. It doesn't matter how high or how low it is, it's crossed off, and so it doesn't affect the median as much. So when the graph is skewed, the mean is pulled that direction, and the median isn't affected by outliers, isn't affected by skewness as much, so the median won't change much. On our last example, most of these players earned, less than 5 million. So we would have had if we would have had a histogram here, we would have had a lot of people in this range and not too many in this range. So it would be skewed right, and the mean X bar is pulled the way of the skew, and the median was more over here. It's not as affected by the skew. So that's what this bullet point means. When the graph is skewed, the mean is pulled right. It's pulled the way of the skew because it's skewed right. the median isn't changed very much. So let's practice here. This is skewed left. So the mean is pulled the way of the skew. So we can maybe anticipate the mean being somewhere here, and the median isn't as affected. So here is the median. Okay, that's for skewed left data. The mean is pulled left. It's pulled the way of the skew. For symmetrical data, or for a normal skewed distribution, that's symmetrical data, they're very similar, the mean and the median. Both of them are in the middle of the data. For skewed right, and that's what we saw with the salaries there, with the MBA salaries, the mean was pulled the way of the skew. So here would be the mean, and then the median was more over here. So whatever way the skew is, the mean is going to be pulled that way. Okay, that's a big concept here in this statistics class. Salary or money graphs, they're almost always skewed right. Almost all salary graphs are skewed right, and the reason for that is because there are a lot of workers, for example, that, if here's our histogram, there's maybe a few in poverty, we're always going to have that, and then there's going to be, a few more that earn, I don't know, maybe 20,000 to 40,000. Then there's going to be a lot of people that are kind of your average type worker, where they get paid a decent salary, nothing elaborate, but they get paid just fine, And then you get some more here, where the higher you get, now there's a few millionaires and there's a very select few billionaires. So this data is going to be skewed to the right. And all salary graphs are skewed to the right, because you just have fewer that get paid a outstanding amount of money than there are that are to the left. So almost all money or salary graphs are skewed to the right. So when there is symmetric data, being that the mean is so affected by skewness, when the data is symmetric, we want to use the mean. So we want to use the mean, and then with that, the standard deviation when we describe symmetric data. Those are the best two measures for describing symmetrical data. And when the data is skewed, we can't trust the mean anymore, because the mean is so affected by skewness. So when the data is skewed, we want to use the 5-number summary, which again is the median, Q1, Q2, Q3, the maximum and the minimum. So when it's skewed data, we want to use the 5-number summary. When the data is symmetric, we want to use the mean and the standard deviation to describe it. Okay, we're going to talk about this one in class. So now we're going to take a look at this here. At company A, each employee got a $1,000 raise. So if they were earning $30,000, they're now earning $31,000. If they were earning $40,000, they're now earning $41,000. So on and so forth. Each bracket of income got a $1,000 raise. At company B, though, instead of getting a $1,000 raise, they got a raise, but instead it was a percent raise. So if you take 30,000 times 1.03, which is a 3% raise, now the person gets $30,900. This $40,000 person gets a 3% raise. Now they're earning $41,200. Okay, so that's what this chart is saying. What will happen to the mean and the standard deviation of each company's salary? Well, class, if we take a look at this here, the mean of all three of these columns, the mean of this is 58,333. Notice what happened in company A when you got a $1,000 raise, when each of these employees got a $1,000 raise. What happened to the mean? Look at that. It went up $1,000 on the nose, didn't it? 58,000 to 59,000, the mean went up $1,000. Now, taking a look here at the mean of the company B, the mean went up, didn't it? The mean went up. And so I ask you this question: how much did the mean go up by? When we got a $1,000 raise, it increased by $1,000. when we got a 3% raise, class, the mean the mean of company B increased by 3%. This is 3% bigger than this one is. Okay? So if you get a $1,000 raise, your mean increases 1,000. If you get a 3% raise, your mean increases by 3%. So now let's take a look at their standard deviations. The standard deviation of the first column, just going to erase all my marks here. The standard deviation of the first column of the salaries was 24,832. Notice what the standard deviation of company A is. It's the exact same thing, isn't it? And that's just because the spread of the data didn't get any more spread out. Okay? The spread from this to this is the same as the spread from here to here. So that's why the standard deviation, which is the spread of the data, it doesn't change at all when you get a $1,000 raise. It doesn't change because the spread of the data remains the same. However, in company B, the standard deviation used to be 24,832. Now your standard deviation increased to 25,5776. And that's because of the spread of the data grew. This difference to this difference is more spread out than this one is to this one. And what do you think the standard deviation increased by? If you're noticing a pattern here, the mean increased by 3%. The standard deviation also increased by 3%. This is 3% more than this one again. Okay? So, to summarize that slide, when you add a certain amount to each number in a data set, the mean will increase that exact same amount, and the standard deviation will stay the exact same. When you add, there is no change in the spread, so the standard deviation stays the exact same. The mean, however, increases by that exact dollar amount. When you multiply, such as a percent raise, like that 3%, when you multiply each number in a data set by the same amount, both the mean and the standard deviation will increase by that amount. If it's 3%, it increases by 3%. If it's 5%, they'll both be increased by 5%. Okay? So that's the meaning of that slide. Okay, so now taking a look here, this is matching a picture to some of the descriptions that we have based on our data. So we're given, with these three graphs, I would probably start off and say which one is clearly skewed. This one looks roughly symmetrical. This one looks roughly symmetrical. I would say this one is very clearly skewed, and it's skewed to the right. So if it's skewed to the right, I would say that it's very noticeable to me then that X bar is pulled the way of the skew, the mean is pulled the way of the skew, and the median isn't as affected. So on these two, the mean and the median would be very, very close to each other. It'd be difficult to tell them apart. But on variable 1 here, the mean should be significantly larger than the median. So now looking at A, B, and C, which one is the mean and the median clearly different than each other? Well, A, they're pretty close, 6.6 and 6.8. B, they're pretty close, 6.6 and 6.0. C is the biggest difference. The mean is significantly higher than the median, so letter C is our skewed graph. So this one right here is variable 1. Okay? So now for variable 2 and variable 3, it's going to be tough to tell just by the mean and the standard deviation, or just by the mean and the median. So now you're going to look at the standard deviation. You're going to look at the spread of the data. So the spread of this data is about 5 units or so, from 3.5 to 8.5. The spread of this data is from a negative 15 to a positive 25. That's more like 40 units. So this standard deviation is quite a bit higher than this one is. So the standard deviation of 8.65, that's going to be variable 3, because the standard deviation is just so much higher. The standard deviation of 1.3, that's going to be variable number 2. Okay, so take a look at the graph, see if you could find skewness in some way or the other, and whatever way the skew is, it pulls the mean that direction. If it's symmetrical data, then you got to look at the standard deviation. The higher the standard deviation, the more spread out the data is. And we'll do this one in class when you get to school tomorrow. So let me know if you have any questions when you get to class tomorrow, and I'll try to make more sense of this if you're stumbling in some way.